Okay, so what does this theorem say? So there are two important parameters. So this is a drift theorem again, so you have some notion of distance. So each individual has, so you measure a distance from any point in your search space to some point you want to reach. It could be the Hamming distance or whatever. So this distance function now, in contrast to classical drift analysis, is not a function from the entire population, but just a function from a given individual to the point you want to reach. Okay? So the first quantity that you can want to analyze is the drift of the variation operator. And this is something that is much easier to analyze. So assume that you have a variation operator, for example, bitwise mutation. So you flip each bit with some probability. The only thing you need to calculate is what is the expected change in distance starting from any point to the next point. Okay. So the only thing is that you apply the variation operator and then you get a new distance. So typically when you are close to the optimum, maybe the distance on average will go away. So this is just some random variable, and you need to estimate the moment generating function of that random variable. Okay? So the moment generating function is just expectation of e to the power of some parameter t times the random variable. So this moment generating function somehow represents, when it can be defined, it represents the entire distribution of the random variable. Okay, so you need to know the moment generating function of the drift. So drift now, with respect to one individual, you have an arbitrary individual, you apply variation, you get a new point. So this is typically straightforward to analyze. For example, if you have bitwise mutation, the moment generating function is just a product of the moment generating function of two binomial distributions, which you know exactly. The second thing you need to calculate is what I call the reproductive rate. So this tells you something about the strength of your selection mechanism. So think now about the population here. Now, some individuals might be better than others, so the selection mechanism will create more offspring from certain individuals. Okay, so let's consider now all individuals in your population, and now count how many times did each individual get an offspring. How many times was a particular individual sampled. If you now pick the individual that has the highest number of offspring, you take the expectation of that, so you get what is called the reproductive rate. So the reproductive rate is the average number of offspring of the best individual in the population. And this is a quantity that you can calculate quite easily for different selection mechanisms. So there's, for example, a selection mechanism called tournament selection, where you pick k elements from the population randomly and take the best. So for tournament selection, this reproductive rate is just the size of your tournament. So for example, if you have a binary tournament selection where you have two individuals, this alpha is just 2. So now you have two really simple properties to calculate. The reproductive rate and the moment generating function of the drift. And a little bit simplified, the theorem says that if the moment generating function of the drift is less than 1 over alpha, where alpha is the reproductive rate, then it's going to take an exponential time as a function of your starting position to reach the goal. And this is proved using branching processes and drift analysis. So you can look at different examples. So for example, the type of EA I looked at in the beginning, where you have this tournament selection, you have bitwise mutation rate, probability P, and the population size at least logarithmic in the number of variables. Let's now consider any unimodal function. So a unimodal function means that each search point has a neighbor which is better. Okay? It's always possible to improve. So if you have r different function values in a unimodal function, then the expected time to reach the target will be either exponential, if k is less than e to the power of pn, where p is the mutation rate and n is the number of variables. And it's going to be polynomial in the number of levels and the variables if the population size, no, if the tournament size is larger than e to the power of p times n. So here, if you look at now the parameter space of the algorithm, we have a kind of a strong phase transition between exponential runtime and polynomial runtime. So if this is your mutation rate, and this is the size of your tournament, if you're on the green side, you have polynomial runtime, and the red side, you have exponential runtime.
Sorry, I just want to unpack that. That seems like a relatively useful thing. So, if your tournament size is 2,
yeah,
and your probability, and you got 100 bits, then you're doomed.
Yes. So if you have the typical mutation rate you have is 1 over n, and suppose you have tournament size 2, then your reproductive rate, so this k is 2, which is less than e to the power of pn, which is e. So if your tournament size is 2, and you use standard bitwise mutation probability 1 over n, you have exponential runtime. However, if you increase the tournament size to 3, it's fine, because 3 is larger than e. So just by changing the mutation rate just slightly, you can go from exponential to polynomial runtime. So usually when I do these talks, I make a bet with the audience. Okay? So I show this theorem afterwards. And first I just do some simulations. Okay? Because often I talk to practitioners, and practitioners are used to the fact that these algorithms are kind of unpredictable. Okay? So I tell them, give me one mutation rate and one value of this reproductive rate, and I'm going to tell you whether the algorithm finds a solution or not to one max. So one max basically, you just count the number of one bits there. So I'm not going to use now tournament selection, I'm going to use instead something called linear ranking selection, because this selection mechanism has a parameter that you can change continuously between 1 and 2. Okay, because a more general version of this theorem says that your reproductive rate, if the reproductive rate is larger than e to the power of pn, you have polynomial runtime on these problems. If it's less, then it's exponential runtime. So, what value of, what mutation rate do you want to try? For example, if we try the usual mutation rate here, 1 over n, so 1, and then if you have now a reproductive rate of, let's say, 1.7 or something like that, so similar to humans. Okay? So 1.7